Okay, folks, let's go over what a Lewis acid is. Now, quick review. We have two definitions of acids and bases so far. You've got your Arrhenius, which says your acid gotta have hydrogen. If you're a base, you gotta have a hydroxide, an OH. Bronsted says, not so fast. You gotta have a hydrogen if you're an acid. In other words, a proton, which is a hydrogen is, when it loses an electron, it becomes a proton. It's just that's all it is, a proton. So it's a proton donator. So essentially you gotta have an H, same thing. But you don't have to have an OH to be a base. You just have to be able to accept that hydrogen. So, for example, ammonia, what you catch when you get sick, you catch ammonia. Funny. NH3, ammonia, can pick up a hydrogen. It can gain a hydrogen. So the hydrogen being gained by the ammonia makes the ammonia a base. And that doesn't have an OH, but since it accepts that hydrogen, and we now get an H4 positive, ammonia is a base. Okay, so those are our two definitions so far, but there is a third definition. And this third definition is called the Lewis definition, named after the chemist who did Lewis structures. I'm sure you all remember how fun those were. And same guy, in the 1920s, he said, you know what, here's a definition that doesn't necessarily include hydrogen or hydroxide. And so, because there are some very reactive things out there, and why not include them? This is the 1920s, very inclusive. Okay, we all remember the 20s, awesome decade. So, if you have some things that are very reactive, then why not include those in your acid-base definition? So what's the difference between Lewis definition and the other two? All right, here we go. That's the difference. What? What's that? It looks like two eyeballs. No, those are two dots, two unshared pair. It's a pair of electrons, two unshared electrons, a pair of electrons. And that pair of electrons, that's the key to Lewis acid-base. If you are something that donates an unshared pair of electrons, if you donate these, then you are base. If you accept them, you say, oh, ooh, unshared pair of electrons, I want those, and you take those, you're an acid. So if you accept, you are an acid. All right. Well, I don't get it. That doesn't make any sense. Explain it to me. All right, let's go back to the ammonia, which I just used. Use ammonia once again. So ammonia, if we were to draw the Lewis structure for ammonia, we all remember how much we love those. So the Lewis structure for ammonia, NH3, has 3 hydrogens. Okay? And it has, it had an unshared pair of electrons. And that unshared pair of electrons just sitting out there, you know, they're wild and crazy guys. They're sitting out there going, what are we going to do? What are we going to do? I got nothing to do. Well, they are ready to rock, as long as they have a reason to do so. So let's say there's a hydrogen floating around out here. Poor little lonely hydrogen, so sad, yes it is, so sad. Lonely hydrogen going, what am I going to do with myself? Well, it looks over here and says, one! There is an unshared pair of electrons there. I could get in there, a bond, boom. If it connects here, and here's the nitrogen going, hey man, hey hydrogen, come on. Yeah, I got 2 electrons right here. Don't do anything. You want to connect? Hook up? Yes. All right, now, that goes in here, connects. We're good. We end up getting what we just wrote down earlier. We end up getting an H4. Well, what happened? The nitrogen donated a pair of electrons. That means, according to Lewis, it's a base. Now, it's a base with the Bronsted definition as well. So both definitions can work. You can have acids and bases that overlap different definitions. Nothing wrong with that. The hydrogen is acting as the acid because it accepted that pair of electrons. It said, thank you very much. I'll take those. Acid, base, Lewis and Brunstad. Okay, well, up here we have an equation. This is on the problem sheet. Okay, I'm looking at the problem sheet right here. Problem sheet this is number 6. And here is the equation that asks who's the acid and who's the base here, according to the Lewis definition. Now you can see that there's no hydrogen or hydroxide here. So doesn't look like it can be an acid-base reaction, but it is. Okay, so here's what we got. We've got aluminum with 3 chlorines around it. And you have this chlorine over here. The chlorine, now it's a chlorine negative ion. That means it has 8 valence electrons. It's found an electron, and that's 8 valence electrons around the outside. And, oh, got my L in there. And they're all unshared. It's just by itself right now. They're all unshared. So this pair of electrons here can be donated to somebody. Boom, donated pair of electrons. Oh, gotta be the base. Now, the acceptor here is going to be the aluminum with the 3 chlorines that becomes aluminum with the 4 chlorines. So how did it become aluminum with 4 chlorines? It gained a chlorine. It accepted those. So it accepted this pair of electrons, and they're going to have to rearrange a little bit. You know, you're going to have to rearrange. So we'll have our chlorine, 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 and chlorine, but we now have connected that aluminum to that chlorine by accepting that pair of electrons, that the chlorine is just like, you want them? Use them. Base, acid. No hydrogen, no hydroxide, but still we have the acid base because of that definition that Lewis used that encompasses more species into the acid base family. All right?